Right, and we're back. So, we are learning about higher functions, higher order functions still, right? The awesomeness and usefulness of partial application is evident. If our function only requires us to pass it a function that takes only one parameter, we can just partially apply a function to the point where it takes only one parameter and then pass it. Yeah, and something that we pointed out here is that we're doing stuff in an interpreter right now. And the interpreter does things a little bit different, where we might throw errors when we do partial applications because it doesn't get what it needs to do, how the interpreter works, or interactive. I don't think it's an interpreter per se, it's just an interactive mode. Alright, so now we're going to use higher order programming to implement a really useful function that's in the standard library. It is called the zip width. It takes a function and two lists as parameters and then joins the two lists by applying the function between corresponding elements. Here is how we will implement it. Right. Takes a function and two lists as parameters. Right. So first we take the function and we take the two lists. And right, we return a list of another type, C. Oh, and that's the, it's the tuple, right? The pair. And our edge cases is if one of the two lists are empty. That makes sense. And we don't care about the function, what it looks like here, but here's the structure. We take a function that, yeah, it takes the head of the first list and the head of the second list. Right, we just identify that we are using the heads of those lists, and we apply the function on X and Y. Shit, what was this again? Oh, we put them... Right. Shit, this syntax becomes a little bit confusing now. Right, we zip both of those. How do we know that this is a tuple? Well, did I just assume that it was gonna create a tuple? Zip width. Yeah, and then you just take the rest of the lists. I feel like I'm missing something here. You tried to implement that yourself, but I guess it's a bit spoiled now. Yeah, I don't feel up to trying to implement it myself today. Yeah, I was gonna... No practical stuff. More reading today and trying to figure out. That's how I feel like today. Right, since we take a list of A's and a list of B's, that means that we take a list of C's, and that kind of implies to me that the C has to be a tuple, right? Oh, no. That's the function. Wait. Right. We don't know what the function is. The function could be anything. So, right, if the function is... let's take something easy. Like, if the function is plus or add, we can add X and Y together, and that would mean that both A and B and C would have to be part of the num type. But since we have type inference, we could do that. Yeah, it depends on what the function is. Yeah, that's why the type classes are like, it's any here. We don't specify type classes because we do that through type inference depending on this function. Yeah, we haven't specified what the function is. So the function might return a tuple, a pair. Or it might return the sum of these two variables. Or it depends on what the function does. We can do whatever. That's why this function is called zip with. We're just joining two lists together with a function. I like that, yeah. It creates a lists. It could be a tuple, yeah. For example, if f is zip. Yeah, if f is zip, then it creates a tuple. Because it would be if indeed we did it with if f was zip, that would be a redundant way to do it because we would end up with a list of tuples, and isn't that exactly what zip already does? So this whole function would be kind of redundant, but yeah, with anything else. Yeah, a list of tuples, yeah. That's what we end up with. A list of something that is not necessarily the same as these, since these are not the same. We could, right? These could be the same types, but they don't have to be. That's what the ABC means. They don't have to be the same types. They can be, right? If our function is division, for example, then we could have an int and a float, and we would get a float out, for example. Something like that. We could do something like that. Right, look at the type declaration. The first parameter is a function that takes two things and produces a third thing. Yeah, it's super vague. It's like, yeah, it does something. It's just a number of parameters that matters for that function. Yeah. They don't have to be of the same type, but they can. The second and third parameters are lists. The result is also a list. The first has to be a list of A's because the joining function takes A's as its first argument. Yeah. Argument? Wait. What? Right. The result is also a list. The first list has to be a list of A's because the joining function takes A's as its first argument. As its first parameter. Right? We call them parameters, not arguments. Used. The second has to be a list of B's because the second parameter of the joining function is of type B. Yeah. BB, right? We have to have A here because we have A here. And we have to have B here because we have B here. And C here because we have C here. Exactly. Or list of A's, list of B's, and list of C's. Maybe it is synonymous? Sure, yeah. But I have this vague memory. I don't know if it's real, but I got this memory of... Maybe it's a false memory? Where I thought it was important to call it a parameter instead of an argument. I don't know. Right, the result is a list of C's. If the type declaration of a function says that it accepts an ABC function as a parameter, it will also accept an AAA function. Yeah. But not the other way around. Exactly, yeah, we did notice that. remember that when you're making functions, especially higher order ones, and you're unsure of the type, you can just try omitting the type declaration and then checking what Haskell infers. Haskell infers to it by checking for type with GHCI. Yeah. If you're unsure, you can let Haskell decide. That's the goal, however, seems the best practices is to do it yourself, to be as restrictive as you can, right? If you are gonna do AAA, right, that's more restrictive than ABC. But if your function is just going to be AAA, then you would want to type that out. Right. Because no side effects. In math, argument means something else. I'll take your word for it. I really don't feel like maths today, like more than usual. I wonder why. Right, the action in the function is pretty similar to the normal zip. Action? Actions? Do we really have those in functional programming? The edge conditions are the same, only there's an extra argument, the joining function. But that argument doesn't matter in the edge conditions. So we just use an underscore for it. Yeah. We don't care. And function body at the last pattern is also similar to zip. Only it doesn't do xy into a tuple, but a function on xy. A single higher order function can be used for a multitude of different tasks if it is general enough. Oh, right. So it depends on what your goal is. Do you want to create a generalized function where that you can apply all over the place? Or do you want to be super specific? So it's not best practices always to be super specific. This is more like a helper function, so to speak. And helper functions might be a good idea to be a little bit more generalized. Yeah, multitude of different tasks. Here's a little demonstration of all the things our little zip width function can do. And here we go. Zip width, we add them all together. So yeah, we take 4 plus 2 is 6, 2 plus 6 is 8, 5 plus 2 is 7, and 6.3 is 9. And we take the max out of the 2. Yeah, we choose the max out of each list. That's one thing to do. Right, what do we have? We add them together. Right. We add them together because it's... Yeah, we just join them. We have a list of lists and we join the lists together, or the strings. Yeah, we join the strings together. Bar hoppers, Bass Aldrin. Oh, what is this though? This one is a little bit more confusing. Zip width, we multiply... replicate 5 to... Oh, right. 5 2 times, right? So... Nope. 1, 2, 3, 4... Yeah, that's 5 of them. Replicate 5 times the number 2. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, because this is an infinite list, but... we stop when this list is done. That actually bothers me a little bit, that it's not the other way around. Replicate. My intuition was going the wrong way, I suppose. Yeah. 2 5 times. Right? Didn't we compare that with math the other way? That in maths you would do it the other way around. No, you wouldn't. It's me flipping it around. Yeah. Right? If this was an x, right, you would write 5x. You wouldn't write x5. No, you would write 5x. Oh yeah, it's just in my mind for some reason. I'm flipping it around. Right, and then we have zip width and this. It's a mess. Right, we multiply. Right, we zip width. And it takes function and two lists, right? So the function ends where? Oh, it's right here. Right. It's because we have a list of lists and we... Oh man, that was just extra confusing. Oh, we see what's going on. It's just they do it with a nested list. As you can see, a single higher order function can be used in very versatile ways. Imperative programming usually uses stuff like for loops, while loops, setting something to a variable, checking its state, etc., to achieve some behavior and then wrap it around an interface, like a function. Yeah. Functional programming uses higher order functions to abstract away common patterns, like examining two lists in pairs and doing something with those pairs, or getting a set of solutions and eliminating the ones you don't need. Let's get that one more time. Functional programming uses higher order functions to abstract away common patterns, like examining two lists in pairs and doing something with those pairs. Wait, are we doing something? Or getting a set of solutions and eliminating the ones you don't need. Yeah, functional programming is more abstract in a way. That's kind of the point. Right, we will implement another function that's already in the standard library called flip. Flip simply takes a function and returns a function that is like our original function, only the first two arguments are flipped. Nice. Nice. We'll get in on tab says, look what imperative programmers need to do to mimic a fraction of our power, Kappa. Well, I still feel like this bashing on imperative programmers is still kind of... I find it a little bit off-putting. Yeah. Because, well, what is happening? What is the Haskell compiler doing? It turns it into an imperative, right? It takes our functionally written code and turns it into an imperative structure. So, I mean, bashing on all this imperative when you're built on top of imperative programming, it's like... It's not really bashing. I mean, the text has said a lot of times how superior that functional way is, right? And I would say it's different and it has some definite pros and some cons, right? And I like the comparison between imperative programming. Just the implication that the imperative way of doing things is worse. I don't know. Maybe I'm just reading into things. Yeah, like you say, it's not really bashing. It's just a comparison, which is good since most people learn imperative programming before they come to Haskell. So Contrast and compare for increased understanding, indeed. All right, flip. We take a wait. Yeah, we take a function and we just flip the order. Exactly. Take A and B and we get C, but no. What we get out is we get B and A into C, so we return a function, yeah. Flip, and then we have a function and we return another function where gxy is equal to fyx. Exactly, just flipped around. Very easy. Colgituna says, don't dim the sunshine of functional way with your cons. Of course I will. I want to be blinded by the sunshine by some of my ideas. I don't want to be blinded, but of course, I mean, I'm sitting here reading Haskell, learn you a Haskell. So of course, the benefits is why we're doing this, not the cons. Right. Like I've heard many people say, right? And I can see it, just learning the Haskell way, then going back to another programming language, you can take the positives you get from a functional, it doesn't even have to be Haskell, right? Just from a functional way of doing things, you can go back to your other languages and do it in a functional way and take just the sunshine with you, right? Reading the type declaration, we say that it takes a function that takes an A and a B. Nice. Nice. A and a B. Love that. And returns a function that takes a B and an A. But because functions are curried by default, the second pair of parentheses is really unnecessary because the arrow is right associative by default. Wait, this parentheses? The second pair. Right, A, B, C, B, A, C is the same as O. We could get this parentheses in here. Right, which is the same as, oh right, yeah, that's what I thought, that we didn't even need this parentheses. That's where we were going. I was wondering, why do they do this? Yeah, because you could just do this. However, just style-wise, I would prefer doing it this way. Yeah, I think this looks pretty. Looks great, huh? Right, we wrote that the G function takes X and Y, and it is equivalent to taking the F function and Y and X. Yeah. If that's true, then Fyx is equal to Gxy. Must also hold, right? Yep. Keeping that in mind, we can define this function in an even simpler manner. How can we? Oh, yeah. Oh, shit. Now this again. Yeah, we don't have to define G because we know that we're getting another function. Wait. Flip the function yx is equal to... Yeah, I still don't like this. I see why we can do it, but I don't like it. Because this looks like a liar. This looks like a liar to me. You're a liar. Because the function on yx is not the same as the function to xy. What if our function is division? And I kind of understand why it works. No, I understand that it works. I just don't like it. Because they're looking like a liar. This here makes sense to me. Right. We're returning another function. And we describe that other function. We have a function and we return another function. This looks like we just have another function and we change that function into being another function, which would not be, right? That would be, we take one value and we set that value to something and then we set it to something else. That is what this looks like. And what I learned in the first chapter is that that makes you a liar, according to the Haskell way. F is the same function. It's not. It doesn't look like it. Yeah. It's personal preference. Personal preference, yeah. Here we take advantage of the fact that the function are curried. We call flip f without the parameters y and x. It will return an f that takes those two parameters, but calls them flipped. Even though flipped functions are usually passed to other functions, we can take advantage of currying when making higher order functions by thinking ahead and writing what their end result would be if they were called fully applied. Thinking ahead? Oh no, that sounds awful. Just thinking ahead? Oh man. Thinking? Too much work. Right. We can flip and zip this. Yeah, exactly. So we get the H first instead of the 1 first. That makes sense. Zip with, flip, div. Ooh, is this just an infinite list of 2s? Like 2, 2, 2, 2, 2, 2, 2, 2, 2, 2 into infinity, right? Yeah. Oh. Then divided by 2. I mean, in general, I don't like the flip function at all. I would just instead change positions of these two. Yeah. I would change sides on the lists myself. Yes. Right, maps and filters. Right, map. It takes a function and a list and applies that function to every element in the list, producing a new list. Let's see what the type signature is and how it is defined. Right, map. Exactly, it takes a function. This is the function. It's very similar to what's going on, yeah. And the edge case, of course, is an empty list. Yeah. And we apply our function to the head. And that's our new list. Right. Map the function to... Oh no, it takes the function and it takes the head and the tail of the list. And we apply the function to X. And we put that in this list, which is right. Just applying the function to the rest of the heads of the tails. Of the tail. Wait, doesn't this prepend? Oh no, yeah, it does, because we start in the inner one. Yeah, it does prepend, but we do this thing first, right? So I was thinking, doesn't it just flip the list around? But it doesn't. I was thinking the wrong way. It does prepend, but it doesn't do this first. Yeah, it does this first. It starts from... Yeah, the thing that gets prepended to the list first is the... we're in the bottom of the recursion, so to speak, yeah. We start at the edge case, and the edge case is the empty list, right? And then we prepend... We strip the layers out of our recursion. We start in the inner layer, and then we prepend after. That is a thing that's still gonna take a while to get used to. That it happens. It feels like it happens in reverse order, but it doesn't happen. It's just... yeah, it doesn't happen at all. It's just a definition, and that's how the definition works. Polygon tabs as maps are familiar to you from Path of Exile. Basically the same thing. Actually, I mean, it's not as far off as one would think. The maps from Path of Exile. Because on the maps, you add a lot of functions to them that then gets added to the area where you go in and play. So yeah, they're not completely separate. Like, you can find similarities, definitely. Even though the general sense, the map in Path of Exile, it's like a map where you look in an... what's that called? An atlas? Just looking at an actual map, a representation of how the world works. Looking for streets and where stuff is. Map is... this is a verb, right? This is more similar to the verb where you map things out. Not the noun. Yeah, verbs and nouns. Right, the type signature says that it takes a function that takes an A and returns AB if a list of A's and returns a list of B's. Yeah, exactly. It's interesting that just by looking at a function's type signature, you can sometimes tell what it does. Map is one of those really versatile higher order functions that can be used in millions of different ways. Here it is in action. Yeah, map, I've touched on it before in Python, because Python has taken this map thing and started doing that as well. Spoiler, filter is also a verb. I was kind of expecting it, wasn't I? Yeah, verb. Which is interesting that we have verb things in a functional language where we don't tell the computer what to do. We're not supposed to tell the computer what to do. But here we're telling it to map this function to this list. In English it becomes like a verb thing. And that is what it looks like. Map this function to this list. Very looks like a imperative semantic structure, not a syntactic, but yeah. Is also a verb. Yes, it is. Right, here it is in action. Map, +3 to all of the things. Map, give an exclamation point to everything. Right, map, wait. Oh right, map replicate 3 to this list. So we do it 3 times. Yeah. And then we have these nested functions that I feel too tired to go through them, but we're just doing the same thing for nested stuff. Oh, this one was easy though, yeah. Just grab the first for all of these pairs, tuples. Nested loops makes my head hurt today, so we're just gonna skip over the nested lists. Sorry, nested lists. Right, you probably noticed that each of these could be achieved with a list comprehension. I didn't notice that, but I mean, we could, sure. Map is easier though, isn't it? Map plus 3 to this list is the same as writing x plus 3 in where x is every item in this list. Yeah. However, using map is much more readable for cases where you only apply some function to the elements of a list, especially once you're dealing with maps of maps. And then the whole thing with a lot of brackets can get a bit messy. Right. This is a pretty good function to just not do complicated list comprehensions. Filter is a function that takes a predicate. A predicate is a function that tells whether something is true or not. So in our case, a function that returns a Boolean value. Okay, and a list, and then returns the list of elements that satisfy the predicate. The type signature and implementation goes like this. Alright, filter. We take a function that looks at an item and returns if it's true or false. Yeah. It's so much easier by just looking at a word. Yeah, we filter everything out that it looks like this. Why does it say P here? Sometimes with these names, right? Oh, because it's a predicate. Oh, it's not necessarily a... Yeah. It uses a different structure. That's why they put the P in, because we put like a guard structure on this. Alright. We filter. We don't care about what the predicate... It's a function, right? It's a function. We don't care about what the function or the predicate is. A predicate is just a function, right? We don't care about what it does, but we have a list, and if the list is empty, that's our edge case, yeah. Right, we filter, we take a function. Right, so if the head wait. P is the function and x is whatever. So x is put into... Wait. Yeah, this is just us going again, right? Yeah, we put the x into the list. This is just a recursion. And however, if it doesn't fit with our predicate, right? If we filter it out, we don't add x to the new filter. Well, x is not in the new filter because we only recursively, right? We'll leave the x behind through the guard statements. Yeah. Because this has to check for a Boolean value, right? So if this evaluates to true... Wait, is that it? If this becomes true, then we do this. Yeah. Otherwise, we do this. Kinda. Pretty simple stuff. If px evaluates to true, the element gets included in the new list. If it doesn't, it stays out. Yeah. Some usage examples. Right, filter everything that is greater than 3. Right? Small, wait. Oh, I was gonna think it was the other way around. But that's, I mean, that's just a quick test away from... You don't have to remember, right? True, false. Which one is it getting? Is it getting everything under than 3 or higher than 3? You just... That's why you check your code always when you program, because it's such an easy mistake to make. That you just... Oh, right. Not 564. I thought it was gonna be... 1, 3, 2, 1, 3, 2, 1. But it's not, right? Because you screwed it up. Trial and error. Right, filter. If it's equal to 3, that's when we keep it. Yep. Oh no, fuck this song. Ooh. Great game. Right. Filter, we take all the even. Yeah, if even is true, we get all of them. Let not null be that x is... Wait. Let not null x be not null x in filter not... Oh man, this is confusing. But yeah, it just takes away everything that has null in it. Yeah. Because we don't need this shit. Get rid of it. Wait, does an empty list return null? That's what's happening, right? An empty list returns null because... Oh man. Too intricate. There we go. It's too intricate. It's like maths. This looks like maths. Not today. You can do it if you like, but... Alright, filter... Oh, right. We... Oh, right. Check if it's one of these in here. You laugh at me because I'm different. I laugh at you because you're all the same. Gay balls. You, this didn't do anything, but here it becomes just gay balls, which is kind of fun, I guess. All of this could also be achieved with list comprehensions by the use of predicates. There is no set rule for when to use map and filter versus using list comprehensions. You just have to decide what's more readable depending on the code and the context. The filter equivalent of applying several predicates in a list comprehension is either filtering something several times or joining the predicates with the logical AND function. Yeah, you can mess around with this, whatever you feel like, I guess. I suppose that you could run tests, right? Yeah, you could run tests to see which one is faster. If you're gonna do something a million times, then running a few tests to see which is faster, and depending on your use case, is the way to do it, right? Since you can achieve a thing 2 different ways, maybe you care more about readability, maybe you care more about efficiency and optimizations. If you care more about efficiency and optimizations, what you do is just you try them both out and see if there's a difference. Well, you can care about your own efficiency as well, and then you just use your favorite, yeah, the one you're most happy with. But there's many different ways to make this decision, sure. Remember our quicksort function from the previous chapter? Quicksort? Oh, yeah. Take the middle and check on the left and right. It was a double recursion, right? We take the head and then we add the bigger and the smaller to each side. We use list comprehensions to filter out the list elements that are smaller smaller than or equal and larger than the pivot. Right, and the pivot was the middle one, right? Yeah. We can achieve that same functionality in a more readable way by using filter. Alright, do we remember this whole thing? Yeah, we take something that can be ordered, of course, otherwise how could we sort them if they're not part of the ord type class? We have a list and we return a list. Empty list is the edge case, right? And we take the head and the tail off the list and, oh man, we did the let in instead of where, sure. Let the smaller sorted and the bigger sorted, yeah. And that's the recursive call where we just filter. Instead of making a list comprehension, we just filter smaller than or equal to x. Or we filter bigger than x. That is actually looking pretty good. Yeah. And this is our list, right? This is the list we create, where we put the head in the middle and put everything smaller to the left and everything bigger to the right. Mapping and filtering is the bread and butter of every functional programmer's toolbox. Oh, it is. So the recommendation is, because this is looking pretty good, just using map and filter instead of using list comprehensions. Something tells me it's more work doing your own list comprehension instead of using map and filter. Yeah. If you just get used to using these. Yeah. It doesn't matter if you do it with map and filter functions or list comprehensions. Recall how we solved the problem of finding right triangles with a certain circumference? I don't remember. I remember that we did it, I don't remember what it looked like. With imperative programming, we would have solved it by nesting 3 loops and then testing if the current combination satisfied the right triangle and if it has the right perimeter. If that's the case, we would have printed it out to the screen or something. Or something. In functional programming, that pattern is achieved with mapping and filtering. You can make a function that takes a value and produces some result. We map that function over a list of values and then we filter the resulting list out for the results that satisfy our search. Thanks to Haskell's laziness, even if you map something over a list several times and filter it several times, it will only pass over the list once. I mean, I don't know if I buy that straight off, right? Sure, but every time for every item in the list, you do a lot of things, right? It's like, just like you could argue that when you do a nested loop, you only loop through the list once, right? The first of the nest, right? The upper layer, you got 3 layers of nests, right? And the outer layer of the nested loop you only do once. It's kind of the same thing here, where it says it only passes over the list once. But I don't know. Sure. I guess it looks prettier, right? If you do it in Haskell, it looks way prettier in the code. It only looks, right? You don't have to create the nests the way you would have to in an imperative language. All right. Let's find the largest number under 100,000 that is divisible by 3,829. To do that, we'll just filter a set of possibilities in which we know the solution lies. Right, largest divisible. Integral. Right, largest divisible. We take, wait, head. We filter the... Oh, right. Yeah, we filter and then that's the function. P is exactly where the remainder is 0 divided by this. And this is the list where it shows up. Right, and we start from 100k. Because we will run into, since we're having integrals, when we run into 0, it's over. Yeah, it's over. We're done. All right. We first make a list of all numbers lower than 100,000, descending. Yep. Then we filter it by our predicate, and because the numbers are sorted in a descending manner, the largest number that satisfies our predicate is the first element of the filtered list. Yeah. We didn't even need to use the finite list for our starting set. That's laziness in action again, because we only end up using the head of the filtered list. It doesn't matter if the filtered list is finite or infinite. Yep. The evaluation stops when the first adequate solution is found. Oh, right, since we're looking for the largest. Yeah, we're not looking for all of them. We just stop when we're done. Right, next up, we're going to find the sum of all odd squares that are smaller than 100,000. Maths. All right. But first, we'll be using in our... because we'll be using it in our solution, we're going to introduce take while function. This looks very much like a while loop. It takes a predicate and a list and then goes from the beginning of the list and returns its elements while the predicate holds true. Once an element is found for which the predicate doesn't hold, it stops. If we wanted to get the first word in the string, elephants know how to party. Maybe they do. I haven't hung out with a lot of elephants. We could take while... All right, that's not equal to a space. Right. That's not equal to, that is what this icon means. That's the function. Right, elephants know how to party, and it would return elephants. Yep. Okay. The sum of all odd squares that are smaller than 10,000. First, we begin by mapping the squared function to the infinite list. Right, we can just start with 1. I remember that. We don't have to set it to 1, 2, and then ... We can just say 1 ... Then we filter them so we only get the odd ones. And then we'll take the elements from that list while they are smaller than 10k. Finally, we'll get the sum of that list. We don't even have to define a function for that. We can do that in one line in GHCI. Right. We take the sum of... Right. Take while it is smaller than 10k. but we filter, and we have to make sure that we have odd and we map it to the list. Oh man, intricate stuff. Predicate is also math. Oh. Right. I think, yeah, that Python has been very inspired by functional programming languages, because this is how they want you to do Python as well. Right, if you look for Python tutorials, it really much follows this structure. Alright, so first, it's always a good idea, I think, to start from in Haskell. What I'm learning is that we don't start over here. This is a confusing place to start to look at these expressions. The best way to look is in here. As far in as you can, right? So what do we have? We have an infinite list that we have squared. We have squared the entire infinite list. And we filter out, so we only take the odd items from this infinite list. And then we only take it when it is less than 10k. And finally, if we think like an imperative language, right? Thinking like an imperialist, yeah. And then we take the sum of all of this stuff. If you want to think about it like an empiricist, right? It's not, but we don't do any of these things because we have defined, right? We have defined what the sum of all this is in a functional way. We're not doing the things. List of positive square numbers. Right. Not... Wait. Positive? Yeah, since we start with 1 and then go into the infinite. And we have squared the numbers. Right. The functional way of thinking about this, that this is a list of positive square numbers. It's not that we take an infinite list, which is... Map is a verb, right? So you'll have to excuse me for automatically going the imperialist way to think about things. Because we have this verb, and this verb, and we have this verb. Yeah. There's a lot of verbs here if we're supposed to think in a functional way. There's too many verbs. Too many verbs. Right, awesome. We start with some initial data, the infinite list of all natural numbers, and then we map over it. And look at this, more verbs. Filter it and cut it until it suits our needs, and then we just sum it up. We could have also written this using list comprehensions. Yeah, I kind of like the map and filter more than list comprehensions because the syntax becomes way easier up here. Unless, I suppose, if you get super used to list comprehensions, you might prefer doing it this way. Yeah, list comprehensions feels more powerful. So probably an endgame goal would be to do more list comprehensions for personal growth, I guess. It is a matter of taste as to which one you find prettier. I find this one prettier, but I find this one more powerful. I don't know. Again, Haskell's property of laziness is what makes this possible. We can map over and filter an infinite list because it won't actually map and filter it right away. It'll delay those actions. Only when we force Haskell to show us the sum does the sum function say to the take while that it needs those numbers. take while forces the filtering and mapping to occur, but only until a number greater than or equal to... oh, right. Number greater than or equal to 10k is encountered. I read that wrong, but that's... I always do that. That's not specific for Haskell. Like, this thing, I always, like, get it mixed up. Luckily, it's an easy fix to make, right? Always test your code. Power corrupts. Can you handle list comprehensions? Actually, we had an interesting discussion about that a couple of weeks ago, that might be a misnomer, that power does not corrupt. They pointed out that, right, if power always corrupts, then power never corrupts. No, we have this idea that I found very convincing, is that people are corrupt to begin with. When they are put in a position of power, they will just utilize that for, like, the behavior that we call corrupted behavior only becomes visible when you are in a position of power. But people are corrupt. It's not the power that corrupts us. We already are like that before we end up with the power. So yeah, we're already corrupted. And the power just lets us do what we want to do, I guess. Yeah. For our next problem, we'll be dealing with Collatz sequences. I have no idea what that is. We take a natural number. If that number is even, we divide it by 2. If it's odd, we'll multiply it by 3 and then add 1 to that. Wait, why are we doing this? Take a natural number. If it's even, we divide by 2. If it's odd, we multiply by 3. Then we add 1 to it. Very strange. We take the resulting number and apply the same thing to it, which produces a new number and so on. Oh, right. This is just theoretical maths, right? Is that what Collatz sequences are? Just theoretical maths. What if we just take this arbitrary rule and apply it? What happens? Colgatinotab says, oh no, the world will tremble when you become familiar with list comprehensions. I mean, I have already, right? I had a head start on that because, yeah, list comprehensions is a big deal in Python as well. Collatz sequences are also math. Yeah, theoretical math, right? In essence, we get a chain of numbers. It is thought that for all starting numbers, the chains finish at the number 1. So if we take the starting number 13, we get this sequence. 13, 40, 20, 10, 5, 16, 8, 4, 2, 1. Yeah, exactly. 13 multiplied by 3 plus 1 equals 40. 40 divided by 2 is 20, etc., etc. We'll see that the chain has 10 terms. Now that what we want to know is this. For all starting numbers between 1 and 100, how many chains have a length greater than 15? First off, we'll write a function that produces a chain. Yeah, this is theoretical maths. Definitely. That is an open problem. Okay, I mean, I don't know maths, all right. We take we chain them. We take an integral a, sure, and we return a list with the same type. That is a member of the type class, right? And we stop when we chain 1 and have a list of 1. Yeah, that's equivalent to the empty list, whatever. Right, and for n, we take even. If we get our even thing, we add n to the chain. But n divided by 2. If it's odd, we add n to the chain, but n is multiplied by... no, wait. We do actually add n to the chain, but the resulting, this is what we do next. Yeah, we call it the next item in the list. Yeah, because we have to calculate the next item on the list, right? Let's say we have 40 here, and it's 40. Boom. Since it is even, we divide it by 2 for our next item in the list. We add n, so we add 40, and then we get 20. Boom. So here it's even again. We add 20 to the list, and we divide by 2, and we do it over again until we get to 5 here. 5 is odd, so then we call this thing. Colgate Uno tab says whether all starting numbers end at 1. Yeah, like I said, no maths for me today. Yeah, I'm not gonna go into theoretical maths today, like not at all. Because the chain ends at 1, that's the edge case. This is pretty standard. This is a pretty standard recursive function. Right, chain for 10, we get all the numbers. Chain for 1, we get 1. Chain for 30, it ends in 1. Yay, it seems to be working correctly. And now, the function that tells us the answer to our question. Right, num long chains, right? What was our question again? How many chains have a length greater than 15? Right, we just take an easy function where we check the length of all, right? Or was it 100? 1 and 100, yeah. We just go through all of these from 100 to 1. And we just keep them if the length is longer than 15. Yeah, that's pretty straightforward. Pretty straightforward. Hello, Mike Kraftchick. Nice to see you again. How are you doing? How have you been doing? Life treating you well? Isn't all maths theoretical maths? Oh, it's like an abstract where you do maths for the sake of doing maths, right? Right, collect sequences, you just do this because. You can do maths for different reasons, right? You can look at someone throwing a basketball and figuring out the arc and stuff like that. That's more, right? Then you're looking at physics, where you use gravity and whatnot. This is just pure maths, if you want to call it that. Theoretical maths, pure maths. These numbers don't represent anything. We just do the math for the sake of the math. But you can do math with many different motivations. And I would guess that most math that happens is just simple plus, minus, multiplication, division, and usually I would guess it's a monetary value where you count money in one way or another. That's probably the most common type of math. I would say, I don't know if I would call that theoretical in this context. Mike Kraftchick says, what kind of programming department is this and what language is it? This is Haskell, yeah. We're reading the book Learn You a Haskell. It's available on learnyouahaskell.com. And it's functional programming, if that's the department you're talking about. Yeah, I'm trying to learn to think like a functional programmer. It's difficult. Yeah. Right, we map the chain function to all of these, yeah. to get a list of chains, yeah, which are themselves represented as lists. Then we filter them by a predicate that just checks whether list length is longer than 15. Once we've done the filtering, we see how many chains are left in the resulting list. Yep. Note, this type has function of has a type of num long chains integer because length returns an int instead of a num. Yep. For historical reasons. I still don't know what I think about that. Part of me wants to be restrictive. I guess that's what I want to be. I want to be restrictive. But I don't know. But I can imagine that there could be a discussion to be had rather than just saying it's historical reasons. If we wanted to return a more general num a, we could have used from integral on the resulting length. Exactly. We can do that if we need to. Mike Kraftchik says, it doesn't look so terrible. I recently had a discrete Fuller transformation in class. I have no idea what that is. A discrete Fuller transformation? Sounds like math. Right, where are we at? This feels... Oh, we're getting to lambdas. All right, so let's finish up with the maps. Using map, we can also do stuff like map. Right, multiply an endless list that starts with 0. If not for any other reason than to illustrate how currying works and how partially applied functions are real values that you can pass around to other functions or put into lists. You just can't turn them into strings. Yeah, exactly. You just can't turn them into strings. So GHCI would, the interactive Haskell would not like this because this is weird as shit. But it's a partially applied function, right? So we could play around with this. Yeah, we could play around with this. We just need to add something. A parameter. There we go, a parameter. Colgatino Tab says, I like it more free. I like it more free and let coder restrictor type declarations if they want to. Yeah, I think that's probably the best idea, right? To have the compiler be as broad as possible. And yeah, let the programmer do the restrictions instead of having them, well, I suppose. Discrete Fourier transform is used to store audio signals. Oh, interesting. I have not touched that. Also, just gonna move over to something else. All right. Where were we? Partially applied functions are real values that you can pass around to other functions. You just can't type them into strings. So far, we've only mapped functions that take one parameter over lists like map multiply by 2 to this list. To get a list of type num, right, type class of num into a list of nums, yeah. But we can also do map, all right, here we are, without a problem. Indeed, yeah. What happens here is that the number in the list is applied to the function multiply, which has a type of num a. Wait, why does it have that? Oh yeah, because it takes multiply takes two and it returns 1, right? You need to have one number and multiply with another number to get another sorry, not a number. Applying only one parameter to a function that takes 2 parameters returns a function that takes 1 parameter. If we map multiply over the list, this endless list, we get back a list of functions that only takes 1 parameter. Yep, so num a. Wait. Oh yeah, exactly. It looks a little bit confusing because we have always done with applied function stuff. We have used parentheses, but we don't have to do that because multiply by whatever, we don't need more than an a here to define that. My crafty says, except that the pattern for this transformation looks terrible. Does it looks terrible? I mean, how do you mean when you say it looks terrible? I guess we can just make a quick check that... Where was it? Color transformation. We can probably just do this. Boolean even. And we check an image. Well, that didn't help. Fourier, not... Alright. Oh man, now we're having math again. Oh no, maths! Take it away from here. Alright. This function produces a list like the one we get by writing... Exactly, yeah. This would be the list. Right, list of funds. Why is that a list of funds? Where we can multiply... Right, we can create the diagram where we can multiply stuff with anything. List of funds. Oh shit, I don't remember what this is. What is the 2 exclamation points again? Exclamation marks, sorry. Getting the element with an index. Ah, index. So this is the 4th. From our list returns a function that's equivalent to 4 multiplied. Wait. Then we just apply 5 to that function. So it's like writing 4 multiplied by 5. Wait. With the index 4? Isn't this a mistake? Shouldn't this be 15? Why not? Right? 1, 2, 3, 4. Index. No, we start from 0. Damn it. Of course we start from 0. And this is 0. I got confused. Yeah. When we look at lists, we always start at index 0. We don't start at index 1. I knew that. It is time to go to lunch though. Because we're gonna start looking into lambdas. I've heard of lambdas before, but I have no idea what they are. So that's gonna be completely new. Oh, actually, now that I see this, basically anonymous functions. You know what? I have seen lambdas before. It's a one-off function, kinda. Anonymous, that we create a function within wherever we are, but we don't give it a name. Haven't we done that before already in Haskell? I don't know. Colgate tabs says that's how programmers do stuff. Yeah, we start our index at 0. That is what we do. Alright, so thanks for hanging out. And yeah, have a good one. And see you next time, yeah. Cheers.